Hello everyone. Today we will cover section 15.6 exercise set. The one I circle in red were done in my lecture videos. I didn't do that many problems. In fact, this section is actually on the shorter one. If we remind ourselves a little bit, suppose we have the domain D here with the surface S, and we want to find the area of S. Sometimes I denote it by only AS. That is equals to double integral over domain D of square root of C sub x squared plus C sub y squared plus 1 dA. If the surface S is managed by z equals to the function of x and y. Maybe I use z as a function of x and y. Okay, now you will see in future that we will write this integral here as double integral over s ds, but that's for chapter 16. Okay, for now we will use this formula here as the area of the surface with domain D. Okay, now let's start. Let's do, for example, question number 4. Number 4, find the area of the surface where surface S is given by z equals to 1 plus 3x plus 2y squared. And the domain D, that's the one on xy plane, is the triangle with vertices 0, 0, 0, 1, and 2, 1. So this is the D, huh? Okay. Now then let's see. What is z sub x? That's 3. Z sub y is 4y. So the square root of z sub x squared plus z sub y squared plus 1 equals to square root of 9 plus 16y squared plus 1. That is square root of 16y squared plus 10. Okay. How about the double integral then? So the area will be the area of surface S is given by double integral over domain D of square root of 16y squared plus 10 dA. Looking at the domain D here, I think, let's see, what is the line here? This is 2, 1, huh? So this is what is good here? See, this is y equals to 1/2 x, right? Or we can also say this is x equals to 2y. I think that's what I will do. So the integral will be from 0 to 1 for the dy, and then integral from 0 to 2y for square root of 16y squared plus 10 dx. Now notice that the integrand is independent of x, right? So that will be just the length of the integral. Integral from 0 to 1 square root of 16y squared plus 10, 1 is not visible, times 2y dy. Then from here I do u sub u equals to 16y squared plus 10. The u will be 16 times 2y dy. I hope you see the reason I write it this way. Okay. And the boundary, the u sub 0, u0 will be 10, u1 will be 26. Okay, then this integral will be integral from 10 to 26 of u to the power of 1/2 times du over 16. Do you notice that? This is our du over 16. Okay, which will be 1 over 16 times 2 over 3 u to the power of 3/2 from 10 to 26. That's 1 over 24, 26 square root of 26 minus 10 square root of 10. I think I can reduce by 2, huh? So 1 over 12, 13 square root of 26 minus 5 square root of 10. Okay, that's for question number 4. Question number 6. Part of the paraboloid z equals to 4 minus x squared minus y squared above xy plane. So that's the when the c above xy plane means the c is greater equals to 0, right? To be more precise, actually it's supposed to be greater than 0. We will use that to get our boundary. Okay, so if the z greater equals to 0, that means 4 is greater equals to x squared plus y squared. That gives us this domain D. That's a disk with radius 2 centered at origin. Okay, that's our D. Okay, now then let's start with c sub x, that's negative 2x, c sub y, that's negative 2y. So square root of c sub x squared plus c sub y squared plus 1 equals to square root of 4x squared plus 4y squared plus 1. Now, you may think you can do this inside the integral. I strongly not recommending that. Okay, now the reason is because we rather set up the integrand properly first. We focus on the integrand, right? This is the integrand. And then we put that into the integral. Okay, double integral over d of square root of 4x squared plus 4y squared plus 1 dA. And you see that, hey, you know what? This integrand is quite similar to, we can convert this into polar integration, right? You see? Okay, because notice that 4x squared plus 4y squared, that's equals to 4r squared, right? Okay, so I can change this into polar integral from 0 to 2 pi, integral from 0 to 2, square root of 4r squared plus 1. As for the dA, it becomes r dr d theta. I hope you remember this. This guy becomes this guy, right? Which happens to be something we need with the r. Yeah. Okay, so when we do u substitution, we get we use 4r squared plus 1 such that the du is 4 times 2r dr. Is that right? And then the limits of integration at 0, at r equals to 0, that's 1. At r equals to 2, that will be what, 17? Now the integral becomes integral from 0 to 2 pi, integral from 1 to 17, u to the power of 1/2, and then du over 8, right? This is our du. over 8. Okay, and the nice thing is it's a rectangle. The integral is independent of theta, right? So the integrand has no theta, the inner integral has no theta, so that will be just the length of interval for the theta, that's 2 pi, right, times 1/8 times 2/3 u to the power of 3 halves, integral from 1 to 17. So that's pi over, what's that, 6? And then 17 square root of 17 minus 1. Okay, that's the surface area of the paraboloid. If you try to sketch this paraboloid, that's 4 minus r squared, right? So it looks like this, where this is the r, this is the c, and then you revolve that around the c-axis. Okay, so the d is actually this here. That's the d. Okay, that's for number 6. I think these are still quite simple, but through these simple examples here, I want to make sure that you follow the details, the procedure. Okay, do the z sub x, z sub y, take a look at the domain, and then put them together into the double integrals. Okay, don't do them all at once. No, it's impossible. It's impossible. Okay, yeah. Now let's go on. Number 10. Part of the sphere that is above z, above the plane z equals to 1. So we have that sphere, number 10. We have surface x squared plus y squared plus c squared equals to 1. So I can write that z squared equals to 1 minus x squared minus y squared. C equals to, supposed to be plus minus square root of 1 minus x squared minus y squared. But since above c equals to 1, it means the c is greater equals to 1, right? Now that implies we only take the positive branch, and even the positive branch should be greater than or equals to 1. Okay, should be greater equals to 1. I'm sorry, it should be 4 here. This is 4. Yeah, because if that were 1, the radius is 1. Anyway, okay, then when I try to solve this, I will get 4 minus x squared minus y squared greater equals to 1. I square both sides, okay? And then I get 3 is greater equals to x squared plus y squared. So this is a disk with radius square root of 3, center at origin. For z greater equals to 1. So in 3D, you imagine if you have a sphere with radius 2, okay, sphere with radius 2, and then you cut it at z equals to 1. Okay, now rotate this. When you rotate this, you will see a disk. Okay, so that's the disk. In 3 dimension though, in 3 dimension, it seems like it's touching the base, but no, it's not. It's not. I think I want to emphasize it by saying this way. Yeah. Okay, it's like in the air with z equals to 1. Okay. Well, anyway, so let's start. Z sub x will be, instead of doing it that way, let's do it this way. You know what? So I will do the c squared equals to 4 minus x squared minus y squared. So 2c sub x, okay, I do the partial with respect to x, I get negative 2x. Is it right? And then z sub x equals to negative x over z, while c sub y will be negative y over z as well, okay, by symmetry thingy, right? And therefore, the integrand square root of c sub x squared plus c sub y squared plus 1 will be square root of x squared plus y squared over c squared plus 1. But what is our c squared again? Our c squared is, this is square root of x squared plus y squared plus c squared over c squared, right? Now notice that the numerator is basically 4. This guy is equal to 4. Okay, so that is equals to square root of 4 is 2 over c. In this case, square root of 4 minus x squared minus y squared. By the way, you can just also do it regular way. If you do it regular way, then of course we take the positive branch only, right? So z equals to positive square root of c minus x squared minus y squared. So c sub x will be negative 2x by chain rule over 2 square root of 4 minus x squared minus y squared. That's negative x over square root of 4 minus x squared minus y squared. Now, if you prefer to do it that way, that's totally fine. Okay, but I want to identify that negative x over this guy here is negative x over z. Notice that this guy is basically our z, right? Okay, so instead of doing the partial derivative with respect to x from the z, you can also do implicit differentiation type, okay, which I employ here. Okay, so that way you keep the z until very end, you substitute that in terms of xy. Now the second method that we did here, we change everything into xy first and then do the partial respect to x, right? So either way you will get the same result. Now I show you this second method simply because I want you to enrich yourself. Okay, enrich yourself. Now we now have the integrand already. Now let's put it in. So the area of surface S will be double integral over d of 2 over square root of 4 minus x squared minus y squared dA. However, you also notice that this is better done in polar integration. So integral from 0 to 2 pi, integral from 0 to radical 3, 2 over square root of 4 minus r squared, r dr d theta, right? Notice that the integrand and the inner integral is independent of theta, so that will be just the length of the integral, 2 pi integral from 0 to radical 3 of 2r dr over square root of 4 minus r squared. Now then I use the substitution, u equals to 4 minus r squared, so du equals to negative 2r dr, u at 0 is 4, u at radical 3 is 1. Okay, and my 2r dr will be substituted by negative du, right? 2 pi integral from 4 to 1 negative du over u to the power of 1/2. Or this is 2 pi integral from 1 to 4. That way I get a positive coefficients, u to the power of negative 1/2. When I integrate that, I believe I will get 2 pi times 2 u to the power of 1/2 from 1 to 4. Okay, that's 4 pi. Square root of 4 is 2, square root of 1 is 1, so that's just 4 pi. Oh, I didn't expect that though. I wonder if I make any mistake. Seems to be okay. Yeah, so it's just too nice. It's just too nice. Yeah. By the way, we are basically getting the area of this part here. This part. Okay. If you have a circle with radius 2, we only get the one. Let's say this is c. This is the z equals. This is the z-axis. Okay, and then we get the part at c greater or equals to 1. Only this part here. So not the full semicircle is less than semicircle. And then you rotate that part. Okay, so that's what we get. That's for number 10. Let's see more. Oh, I think that's all, huh? Number 24. This is a classic question, actually. The figure shows the surface created when the cylinder intersect with another cylinder. So this cylinder here, the first surface y squared plus c squared equals to 1. This is a cylinder parallel to x-axis. Okay, I think if I color that, if I try to color that, this will be the blue one. Hold on. Parallel to the x-axis. No, my bad. Not the blue one, the yellow one. Will be the yellow one. This one here. Okay, but it has the backside also. And x squared plus c squared equals to 1. That is actually the blue one. Is parallel to, this is parallel to y-axis. Instead, y-axis is the center axis of that cylinder. Okay, in the first surface, y squared plus c squared equals to 1. Because it's missing the x variable, then it is parallel to x-axis. Now the hard part is to imagine the intersection. Good thing they already graph it for us, and we get this intersection that actually consists of, if you think about that, it consists of how many parts? So in the first octant, there are actually 4 parts in the first octant. So if we draw the first octant, if we see that from above, x and y, you see this part here is the blue. If you see that from above, that's the blue part. And then this part here is the yellow part. Okay, so even if you see that from above, you have this part here. You can't really see, huh? let me use slightly different, a bit darker color. So this part here, okay, is this, if we see that from above. And then if we see this from above, it will be this part here. I don't know if you can see that. It's this. Okay, so but we can also see that these four parts here actually symmetric to each other. Okay, they have the same area. So what I will do, why 4 times? Well, because on the top you have this guy and this guy are symmetric, right? And you have the bottom one also symmetric. Okay, all these four, the top and the bottom, are symmetric. Okay, now and then later on I will multiply by so in the first octant we have 2 parts, right? In the first octant we have 2 parts. Later on I will multiply by 8. In other words, the area of the whole surface will be 16 times the area, 16 times the area of D, if I call this my D. You know what? I don't want to call that D. Call that S1 then. So because I don't want you to confuse that with the domain D. Okay, so this is my S1 here. This part. Okay, this part. Maybe I erase them first. So if I draw further, and then so my S1 is this. This is my S1. Okay, now looking at that S1, I think I want to say S1 in the first quadrant, in first octant, octant 1. Okay, if I solve for c squared equals to 1 minus y squared, z equals to, because it's in the first octant, then the square root is positive. We take the positive branch, right? Such that c sub x is 0, but c sub y is negative 2y over 2 square root of 1 minus y squared. The 2 cancels. Okay, and then therefore square root of z sub x squared plus z sub y squared plus 1 is equal to 0 squared plus y over 1 minus y squared plus 1. But this is equals to the square root of y squared plus 1 minus y squared over 1 minus y squared. That's basically square root of 1 over 1 minus y squared, right? That's the integrand. So this is 16 times double integral over domain D, the triangle, the shadow of S1 in first octant, okay, of 1 over square root of 1 minus y squared dA. Okay, let's draw the domain D then. The domain D in this case is this guy here. This is 1. This is y equals to x. So this is 16 times integral from 0 to 1, integral from 0 to y, 1 over square root of 1 minus y squared dx dy. I want to do it that way, but seems like the domain is incorrect. The dy is wrong. Oh, I'm sorry. If I want, no. If I want suppose I want to do dy dx. dy dx. So the y will be from 0 to x, right? But I think it's actually harder to integrate this way. Is it right? Oh, that's sine inverse, huh? Is it right? That's sine inverse, that's right. So that's 16 integral from 0 to 1. Okay, the integral of this is sine inverse y from 0 to x dx. Right? Okay, and then this will be 16 times integral from 0 to 1 of sine inverse x minus sine inverse 0 is 0. Let me write it down first. You know what? Sine inverse 0 is 0. Dx. Now, how to integrate this further is another story, but I will do integration by parts. The derivative of sine inverse x is 1 over square root of 1 minus x squared. This is x here, so that will be 16 times x sine inverse x from 0 to 1, which is just sine inverse 1 later on, minus integral from 0 to 1 of x over square root of 1 minus x squared dx, where I will do integration by substitution. Okay, I will do it another method later on, but for now, let me just go on. This is x sine inverse 1 sine inverse 1, that's sine inverse 1, minus, if I do u substitution here, u equals to 1 minus square root of 1 minus x squared. So du equals to negative of x over square root of 1 minus x squared dx. So u sub 0, u at 0 is 1, u at 1 is 0. So that's integral from 1 to 0 of negative du. Like that. Okay, so this is 16 integrals, 16 times sine inverse 1 minus, or actually minus integral from 0 to 1 du. Oh, that's just 1. Sine inverse 1 minus 1, which is quite impossible though, because it's supposed to be area, so it's supposed to be positive. I must have made some mistake somewhere. Did I? I start to question myself. Let's see. If x equals to sine y, the derivative of x is dx equals to cosine y dy. So 1 over cosine y equals to dy dx. Yeah, dy dx. So 1 over square root of 1 minus x squared. This is cosine y. Like sine inverse x equals to y. So the derivative of sine inverse x is that, so the integral of 1 over square root of 1 minus x squared dx is equals to y, which is sine inverse x plus 1c. So that's correct. Let me check my work again. Well, sine inverse 1 at most 1. Oh, hold on. Sine inverse 1. Duh, what am I doing? That's not sine 1. It's sine inverse 1. Sine inverse 1 is pi over 2. So I'm correct. Sorry. So that's pi over 2, which is more than 1 minus 1. Okay. So this is 8 pi minus 16. Oh, I thought I was wrong. My bad. Okay. Now, I think my issue earlier was this. How do I set this up? Okay, integrating with respect to y first requires me to memorize what is the integral of 1 over square root of 1 minus y squared, the integral of this respect to y. Now, is there any way for us to avoid that? Let's try another way. So another method is we reverse the order of integration. So let's say this area of S equals to 16 times integral from 0 to 1 for the dy. And as for the x, the x will be from y to 1. Y to 1 dx. Okay, that's 1 over square root of 1 minus y squared. But that will give us 16 integral from 0 to 1, the length of the interval 1 minus y over square root of 1 minus y squared dy. Okay, which will give us 16 times integral from 0 to 1 of 1 over square root of 1 minus y squared dy minus integral from 0 to 1 of y over square root of 1 minus y squared dy. This will be, oh, still, we still need to do that sine inverse thing. So this will be sine inverse y from 0 to 1. And the guy here is basically the same to what I did. This guy here is the same to this guy here. Is it right? That's just the same. That will give me 1. So yeah, we will get the same result anyway. Okay, and yes, from this example, you see that we cannot avoid memorizing the integral of that ugly guy that give us sine inverse. Okay, that give us sine inverse y in the red color and sine inverse x. Yeah, sine inverse y also in the blue color. Yeah, it seems like we cannot avoid that. Okay. Now, if we just want the full part in the first octant, then you don't multiply by 16. And the area in the first octant is only this part. That's the area. If we don't multiply by 16. Okay. That's for this section 15.6. The idea is actually quite simple. The area is double integral over domain D, which is the shadow of surface S on the domain, the coordinate system in the domain. In this picture, that's the xy plane. Okay, but then we have integrand that looks like this. What we have done so far in all these questions, I basically apply that to different cases. Okay, now this is for 15.6. Let me stop the recording here.